doing on the Fermi Bubbles at STSCI. Oh, there we go. And so I've been doing that work with my collaborators listed here. And I just want to first start off with possibly the most famous scientific image of the Fermi Bubbles, and that is the gamma ray emission, where these two orange blobs in this map are what we refer to as the Fermi Bubbles. So they are giant plasma bubbles coming from the galactic center of the Milky Way. And we don't only see them in gamma ray emission, we see them in various other wavelengths, including X-ray, which I've plotted on top here. And as you can see, these images match up very well. So the X-ray and the gamma ray are most likely related. We also see them in atomic hydrogen emission, or in this case, the lack thereof, where I've plotted on top of here the blue, which is the atomic hydrogen emission. And as you move from the outer left edge of this image, you notice the disk gets thinner and thinner as you move towards the galactic center. So I believe this is evidence for nuclear outflow near the galactic center. So this is just an artist's image of what we believe the Fermi bubbles look like. And you can see that they are very large on the sky, and also in length. They extend about 20 kiloparsecs in length. And then from various UV absorption surveys, we also have model-dependent outflow velocity of about 1,000 kilometers per second, a wind age of 6 to 9 megayears, and a mass outflow rate of 0.2 solar masses per year. So that's great. We're starting to get some kinematic information about the Fermi bubbles and what's going on inside of them. But we really want to know how they formed. So there are two main camps in formation theories. There's a camp that believes they form via star formation, and there's a camp that believes they form because of the supermassive black hole in the center of the Milky Way, Sagittarius A star. So the star formation camp believes that a massive amount of star formation that's been going on in the galactic center formed the Fermi bubbles over the past 30 to 100 megayears, depending on the model. And that happened through strong stellar winds and supernova explosions. Whereas with Sagittarius A star group, they believe that the bubbles formed via an accretion disk wind or jet activity over the past few megayears. So very different time scales for these two formation models. And both of these formation models have the necessary energetics to form the Fermi bubbles, but just on those very different timescales. And more recently, a lot of evidence has come out that Sagittarius A star is more likely to have formed the Fermi bubbles. And I've just listed a few things here as those pieces of evidence. And one of those is what I showed in the last slide, that they have an observed wind age that's a little model dependent, but essentially it shows an age of 6 to 9 megayears. And there are a couple different models that show that wind age. And so that's more in line with the Sagittarius A star formation model of a few megayears. And then on top of that, if star formation was going on in the galactic center over the past few hundred megayears, let's say, or over the past 100 megayears, we would expect to observe evidence of a large B star population in the galactic center. And we don't observe evidence for a large enough B star population to really say that that's happening. Further, more recent evidence has shown that there's a black hole flare possibly affecting the Magellanic Stream. So to explain that, I'm just going to bring up a figure from Bland, Hawthorne et al., 2019. And in this image, the Milky Way is cutting through horizontally the center. And your eyes are not deceiving you. The galactic north is pointing downwards in this image. And that's because Jos Bland Hawthorne lives in Australia, and that's the way that he likes to put his figures. And on top of this, we have the LMC and SMC system in red. And so this image, you can see that there are elevated H alpha levels and elevated ionization levels in the stream that you're not seeing in other parts of the LMC-SMC system. And so Bland, Hawthorne et al., they show that through some modeling that star formation could not have caused these ionization levels in the stream. And that these ionization levels need something stronger, like a Seifert flare event coming from the center of the Milky Way in the past few megayears. So if that occurred in the past few megayears, then it's also possible that the Fermi bubbles were formed at the same time. Fox et al. 2020, if we just flip this upside down real quick, also shows evidence for that by finding evidence for photoionization occurring in the Magellanic stream, but not in the leading arm. So again, further evidence that a Seifert flare type event in the past few megayears has occurred, which could have formed the Fermi bubbles at the same time. So we want to know how the Fermi bubbles formed and what effect they might have on the Milky Way halo and things like the SMC-LMC system. But we also want to compare them to central outflows in other galaxies. And that's important because for the Fermi bubbles, we have a front row seat to what's going on, and they're very large on the sky. So we can study them in 2 dimensions, in both latitude and longitude. And that's important because when you go to extragalactic science, you typically only have maybe one sight line down the barrel to study central outflows. And so we can use the Fermi bubbles as analogs for other galaxies and their central outflows. Now I study the Fermi bubbles in UV absorption, and this is just an artist's image of what we do. So we typically use distant quasars as our background light bulb in order to measure absorption features from the Fermi bubbles. We can also use stars within our own galaxy, but you need to know their distance very well and their UV properties very well in order to separate out those UV properties from Fermi bubble properties. And so when we're looking at the Fermi bubbles and UV absorption, we're not actually looking at the plasma within the Fermi bubbles. We're typically looking at cooler gas clouds that are flowing through the Fermi bubbles that got caught up in the Fermi bubbles. And so by cool gas clouds, I mean about 10 to the 4th to 10 to the 5th Kelvin here. And when we're looking for these gas clouds, we're looking for gas clouds that are moving faster than plus minus 100 kilometers per second. And that's because when we measure the Milky Way disk rotation, we expect the Milky Way disk to be rotating at about negative 100 to 100 kilometers per second. So anything moving faster than that, we know is moving too fast to be rotating in the disk and is more likely associated with the Fermi bubbles. And so we call those clouds high velocity clouds, or HVCs. So this is just an image on top of the gamma ray emission showing you all of our past sight lines for the UV data. And for previous surveys, I have black circles and black stars indicating UV sight lines for AGN and stars within our own galaxy. And you might notice with all of these black circles and stars that not many of them get to these really low latitude regions of about plus minus 30 degrees. Many of them are either outside of the Fermi bubbles or just at the edges. And so one thing we really want to understand is these low latitude regions, because that's close to the launch point of the Fermi bubbles. And if you want a full kinematic picture of what's going on in the Fermi bubbles, you have to probe these low latitude regions where they're launched. Luckily, Monroe et al. 2016 had this new catalog of bright UV background sources that we can use, and 5 of them fell in these low latitude regions that were very close to or within going through the gamma ray defined Fermi bubbles. So we got some HST cost data on these to look at the absorption features. And I'm just going to show an example of that in the next slide, where I've highlighted in blue on the left the one sightline that we're looking at. And on the right, I'm showing an example of the data where you have normalized flux on the y-axis and LSR velocity on the x-axis. The data are these black lines, and the fits to the data are these green lines. So this is kind of our poster child, which is why I'm showing it, because it actually had 4 detected HVCs in it. And you can see them most clearly in the silicon 3 down here, where you have these 4 dips, 2 blue shifted and 2 red shifted. So again, this is just an example of some of the data that we got, but as a whole, for all of the results, this image summarizes those results, where I've plotted the HVC, or the sightlines that had HVCs detected in color with red shifted or blue shifted indicated by the color. As you can see, these 2 sightlines near the edge and off of the gamma ray defined Fermi bubbles, we didn't detect any HVCs. So putting these together, these new sightlines with the previous studies, we find that about 80% of the pointings that go through the gamma ray defined Fermi bubbles have an associated HVC. Whereas outside of the Fermi bubbles, the pointings that are there, only 28% of them have an associated HVC, which makes us pretty confident just in covering fraction that the HVCs that we're seeing are most likely associated with the Fermi bubbles. Now, we could just study these 3 new sightlines with HVCs on their own, but statistically it's best to combine them with the previous UV surveys. And so we did combine all of the data, and what you're going to see in these next few plots are HVCs that had gone through the Fermi bubbles, the gamma ray defined Fermi bubbles. So I'm just going to start off with galactic standard arrest velocity profiles. And there's a lot going on here, but let's start off with the symbols. So the circles represent the southern Fermi bubble, and the squares are the northern Fermi bubble. We were looking for any asymmetries between the 2 or anything that might be different, amongst other things. And so we also, on the y-axis, both y-axes, we have plotted the max absolute GSR velocity, which is quite a mouthful, but essentially what we did is for every pointing, we took the maximum velocity HVC and plotted it here. So we didn't plot all of the HVCs we detected, only the max velocity one. And then we plotted that against absolute latitude and absolute longitude. So I'm going to start off with the absolute latitude plot first, where, as you can see, as you go further away from the galactic center in absolute latitude, you get a decreasing GSR velocity. And we plotted this line here because we made a linear fit to the data because it was so beautifully fit by this line. So as you go further away from the galactic center, you're getting this decrease in projected velocities. And I just want to say projected velocities real quick because we're going to get to deprojected modeled velocities a little bit later. So then we can move on to absolute longitude, and you might have noticed there's no line plotted here. These labels here, by the way, are the 3 new sight lines that we had in our data set. And the reason there's no line plotted here is because we couldn't find a decent linear fit to this data, and we could not find a strong monatomic relationship for this data by doing a Spearman's row test. So there doesn't seem to be much of a relationship in the way of monatomic relationships for max absolute GSR velocity versus longitude. So overall, we're seeing that things are changing quite rapidly with latitude, but not so much with longitude. Now there's another way that we can plot this up, and that's as if it were on the sky, which is a nice way to look for extra asymmetries between the northern and the southern Fermi bubbles, or any patterns that we might have missed previously. So here I have galactic latitude and galactic longitude plotted up, and this black unfilled oval shape, those are the approximate outlines of the Fermi bubbles gamma ray emission. Now each circle that's filled here is an HVC, and its velocity is denoted by the size of the circle. So smaller circle, smaller velocity. And we didn't see any extra real trends in the data with this plot, but what we did see is a nice trend of decreasing velocities as you went up in galactic latitude here. So it's just another way to visualize the data. So next property I really want to talk about is the incidence of absorbers. So for these plots, I've plotted the number of absorbers per sightline. And I've done it for different ions here, so carbon-2, carbon-4, and then the silicon ions that we were able to detect. And I've plotted absolute latitude and again, absolute longitude. So I'm just gonna start off with the absolute latitude plot again, where you might first notice this 0 to 10 degree bin here, where there is a large number of absorbers per sightline. So that's very close to the galactic center. And then as we go out, we notice this 10 to 40 degree latitude region, there's a sudden drop in the number of absorbers per sightline. And even that has its own slight decrease in the number of absorbers per sightline. So what we believe this is caused by is if you look at the Fermi bubbles, they come to a point near the galactic center. So if you're taking a single sightline through the Fermi bubbles, then you get this region that comes overcrowded, or not overcrowded, but it becomes crowded with these high velocity clouds because they're in a very condensed region. And then as they flow through the Fermi bubbles, they're allowed to kind of spread out. So you get this decreased number velocity or number density. And then as we move to this 40 to 60 degree region, you notice another jump in the number density. And I believe this is because at this point, you're starting to hit the upper boundary of the bubbles. And so you're hitting these interface layers where a lot of these HVCs might be hanging out. So it's a projection effect essentially. Then when we move to absolute longitude, we tried to fit the data again with monatomic relationships, a straight linear relationship. And we didn't see any strong trends again. There was a potential weak monatomic relationship, but there was no strong linear trend in these data. So again, what we're seeing is this strong change in latitude, but a fairly non-changing longitude axis with the current data that we have. So the last topic I want to hit on just the UV data alone is the ion column densities. And this is important because we want to look for any changes in the column densities or their ratios, because it can tell you about ionization or recombination while moving through the Fermi bubbles. So for example, if silicon-2 were being ionized into silicon-4, let's say, you would expect to see that silicon-2 is decreasing and silicon-4 is increasing with latitude. It's not always that simple, but that's a general idea. So in these plots, again, I'm just plotting what you would see in the sky with latitude and longitude. And then the size of the circles represents the log of the column for that ion. Now, we did plot every single HVC in this plot for the column density. That's why you see multiple circles here, with the lowest column density is shaded. And we all have a half circle because that right there is a lower limit. That line was saturated, so we couldn't get an accurate measurement of its column density. So overall, we looked at plots like this. We looked at plots showing absolute latitude, absolute longitude. We looked at ratios for these different ions. And we were not able to see any obvious trends in latitude, longitude for their columns or their ratios. So what does that mean? Well, it could be that these HVCs are moving so fast through the Fermi bubbles that they don't have time to be ionized through their movement or recombine while they're moving through the Fermi bubbles. It's also possible that their ionization and recombination times are so short that we're not really seeing a strong effect as they move through the Fermi bubbles. So I said that's the last piece I want to talk about with the UV alone, the UV data alone, because we also combined our UV survey results with the atomic hydrogen survey results. And we did this because we wanted to look at these low latitude regions, like I mentioned at the very beginning of my talk. And so these low latitude regions are really where the H1 surveys come in handy, because the atomic hydrogen surveys reach very extreme low latitudes in comparison to the UV survey results, which reach the higher latitude regions of the Fermi bubbles. So I'm going to show that here as an example. This is one of those studies in atomic hydrogen by D. Teodoro, 2018, taken with the GBT. And you can tell that the maximum latitude in their plots are plus minus 10 degrees. So they're getting to these much lower latitudes near the launch point of the Fermi bubbles. And in these studies, they've shown that these clouds here are not participating in galactic rotation. And from some modeling, they're more likely participating in a bipolar outflow coming from the galactic center. So we wanted to combine these data and several other H1 survey data with our own UV data to see what trends we could find in the overall kinematics of the Fermi bubbles. So in this plot, I've combined those data where we have GSR velocity on the y-axis and absolute latitude on the x-axis on a log scale. And these open circles and squares, those are the atomic hydrogen data. Whereas the filled circles and squares, those are the UV data.
Trisha, we're not seeing that slide.
Ah, no. Okay, let me get out, and then I'm gonna stop sharing and start sharing again. Let's see if this works. Can you see it now? No? Is this the right, can you see the plot of GSR velocity versus absolute latitude now?
No, it just
blank
says
screen.
Yeah, blank screen.
Ah, okay. Let's see. The only way I found to fix this problem is to try sharing again. In the past, this has happened to me also, and I don't know why. Is it sharing now by any chance?
No.
Blank screen.
Oh no! Oh. Does anyone else have some suggestions? The best I could do is at this point just keep trying to share or sign off and sign back on.
I've sometimes had problems when I'm sharing a presentation that I have like in present mode, but if I exit that and just show the slides
That's what I'm
as
doing
if I was
right
editing
now.
them.
Yeah,
Okay, yeah,
that's not working for some reason. This is the third time this has happened to me. I think it must be my computer.
It may not entirely have been at Trisha's end, because when Jay couldn't see her presentation, here in the rabbit patch, I could see it just fine.
Oh, interesting.
How about now, Chris?
No, can't see a thing now.
Well, I just stopped sharing momentarily, but I'm sharing now. All right. So what I'm gonna try and do is I'm gonna sign off and sign back in and see if that helps. I'll be right back. Okay, so let's see. Can you all see that now?
That did it. Good.
Yay. Okay. All right, last resort worked. All right. So now I can show you the plot of GSR velocity versus absolute latitude. So this is log scale, as I mentioned before. And these open circles and squares, those are the atomic hydrogen data surveys, whereas the filled circles and squares, those are the UV absorption data. And so there's a giant gap here in velocity, and that's because of confusion with the Milky Way disk. As I mentioned a little bit earlier in my talk, for the UV data, we can't measure all the way down to these low velocities because the disk rotation is occurring at those velocities and we can't separate that out. And then you might also notice that there's this peak in the GSR velocity between the data sets around 7 to 10 degrees in absolute latitude. So that peak, you can see that there's some UV data around there and some atomic hydrogen data, and they both have a very similar range in velocities, which is a good thing because we want to see if we're measuring kinematically the same type of flow. And that shows that here. Now in the atomic hydrogen data, it takes this shape of increasing velocity, but there's not much data in this region, this kind of triangular region between the data and the edges of the axes. And so that was shown in Lachman et al. 2020 to be most likely due to acceleration. And so these atomic hydrogen clouds are being accelerated away from the galactic center. And then you get this trend in the UV where they're doing the opposite. They tend to look like they're going down in GSR velocity. However, remember I mentioned earlier on, these are projected velocities. So we have to deproject them to see what's actually happening inside of the Fermi bubbles. And we're going to get to that in just a minute, but first I wanted to talk about the HVCs highlighted in pink here, because these are strange little HVCs. They're actually moving too fast to be contained within the Fermi bubbles. And so I'm going to explain that using a figure from Miller and Bregman et al. 2016, where this is a side view of what we believe the Fermi bubbles look like. And the gamma ray defined Fermi bubbles are in blue and the X-ray defined Fermi bubbles are in green. So if we're on the side view and we're taking two sight lines, this is one at 23 degrees approximately, and this is at 45 degrees. And then we assume that our gas clouds that we're measuring velocities for are coming out radially from the center of the Milky Way. We can see what their projected velocities would look like in this toy model. And we see it around 23 degrees in latitude, we still get a projected velocity towards us. But at 45 degrees approximately, you would expect at a radial motion that you're not seeing much, if any, of the projected velocity. So you should get a projected velocity of about 0 kilometers per second at a latitude of 45 degrees. Now this doesn't happen for the redshifted side, and that's why I didn't highlight them in that previous graph, because even at 45 degrees, you should expect in radial motion to still see these projected velocities that are redshifted. So if we go back to our graph here at about 45 degrees, you would expect a velocity of 0. And you can see if we draw our eyes back to the rest of the data, that these data points here, these HVCs, are moving above the expected velocities just using this simple model. So what does that mean? What are they doing? They're moving too fast to be within the Fermi bubbles, so where could they be? Well, if we take our simple model again and put them in front of the Fermi bubbles, if they have that radial motion, then we get a projected velocity greater than 0. And so it's possible that these gas clouds are actually in front of the Fermi bubbles. And what that could mean is that they're either gas clouds left behind from previous galactic center outbursts. So if the Fermi bubbles are cyclic, then you can get these gas clouds left behind from a previous Fermi bubble formation. And then another idea is that these were gas clouds in the halo. And as the Fermi bubbles formed, they pushed these halo gas clouds outwards. So there's lots of modeling to still be done with that and to try and figure out where exactly these gas clouds are and what they're doing and where they came from. So that's some future work we'll be doing. And so then I kept promising that we would talk about deprojected velocities, so I'm going to do that now. We had one of our collaborators, Ed Jenkins, work on a conic geometry model for us in order to try and deproject some of these velocities and figure out what's going on in the Fermi bubbles. So this model, essentially, it assumes that the Fermi bubbles are two cones coming from the galactic center. It's a simplified model, but it's a place to start. And the idea is we're trying to calculate the probability of finding an HVC with a very specific location and a very specific flow velocity. So we're trying to find the probability of that. And we do that by assuming that the gas clouds come out of the galactic center and that they're spread uniformly in this radial motion along the cone of the Fermi bubbles. And so they can flow at this angle alpha here, away from the galactic center, and we're trying to see if they're at this r, this distance from the galactic center, and what their flow velocity is. This is the deprojected velocity.
Excuse me, Trisha.
Yeah.
Sorry, Trisha. We're still seeing the previous slide, the velocity of hydrogen clouds versus absolute latitude.
Okay. All right, I'm gonna stop sharing and share again. And if nothing else, I can always sign out again. Are you getting a blank screen?
Yes, blank.
Of course. Let me give it a minute. And then escape. Maybe it doesn't like animations. All right, I will sign out and sign back in again, see if that helps. Well, this is nothing if not eventful.
Got it.
Cool. All right, let's hope this continues without any more falters. All right, so you can see the many arrows?
Yes.
Excellent. Okay, so we assume that these clouds are uniformly distributed throughout the cone and that they move radially away from the galactic center to a distance r and a deprojected flow velocity. So these are the two parameters that I'm going to be showing in the next slide, this r and this deprojected velocity. So in these figures, these are probability figures. So the red is high probability of seeing a cloud at that velocity on the y-axis and that distance on the x-axis. And there's 4 different plots here, but essentially on the left column, you're seeing the atomic hydrogen data. And in the right column, you're seeing the UV absorption data. And in the top panel, in the top rows, we're assuming that the clouds have their mass conserved as they move through the Fermi bubbles. And then on the bottom row, we assume that the clouds are allowed to erode as they move through the Fermi bubbles. And so essentially, I want to start off with the atomic hydrogen data here, where in the 0 to about 1 kiloparsec range, we notice in both panels, top and bottom, that the most probable velocities are in the 100 to 250, possibly up to 300 kilometer per second range. And then in the 1 to 2 kiloparsec range, we see that the most probable velocities are on the higher end of that, closer to 2 to 300 kilometers per second. And that's showing the acceleration, which Lachman et al. Also showed in the atomic hydrogen data. And then if we move to the right panels for the UV data, you notice that it's much more sparse, and that's because we don't have a lot of sightlines to fill in all of this nicely. But in the 1 to 2 kiloparsec range, we do see that the velocities are similar to what we saw in the atomic hydrogen, around 200 kilometers per second. And then something strange happens, or at least I thought it was strange. At around 6.5 kiloparsecs, we see a high probability of velocities closer to 300 or 400 kilometers per second, which would indicate that not only are these gas clouds accelerating in this 1 to 2 kiloparsec range, but they're also accelerating all the way up to about 6.5 kiloparsecs. So started looking at this area more carefully and trying to figure out where these data were, this 6.5 kiloparsec region. And we noticed that these two regions are dominated, or this region is dominated by those blue shifted clouds beyond about 30 degrees in latitude. And if you remember from this previous plot, those clouds are the ones that were moving simply too fast to be contained within the Fermi bubbles. We included them in these models because it was a conic shape, so they were allowed to be in the model. But when we go to a more realistic geometry, like the Miller and Bregman geometry, which I showed the actual bubbles on the side view, these are likely moving too fast to be contained within the Fermi bubbles, which means when we go back to these data at around 6.5 kiloparsecs, we're seeing clouds that are dominating this region that are moving faster than they would be if they were contained within the Fermi bubbles. So if we want to look at just clouds within the Fermi bubbles, these probabilities should probably be shifted downwards a bit. And in that sense, we're more likely seeing either a very low accelerating region between 2 and 6.5 kiloparsecs, or a more coasting phase of constant velocity. And that would look something like this from our side view again, where we have this region of acceleration and then either a small acceleration or a coasting phase going on at these higher latitudes. And then of course you have to add in these clouds out in front because they're the ones that are throwing off the graphs. So finally, I'm just going to add some conclusions for you. We don't really see any evidence for deceleration up to about 40 degrees in latitude. And we do see the Fermi bubbles, the number density of these HVCs are decreasing as they flow up through the Fermi bubbles. And that's probably just because they're spreading out in the space. Then there's no obvious kinematic or ionic content asymmetries between the northern Fermi bubbles and the southern Fermi bubbles, and we also don't see much change in the longitude with our current data. And then there are a group of anomalous velocity clouds that likely lie in front of the Fermi bubbles, so maybe I should have NASA change this image to include them. But yes, that's all.
Thank you for the talk. Any questions for Trisha?
Yeah, thanks for a very nice presentation. I want to follow up the last point you made about clouds that are remnants of a previous event. The ones on the near side would be pretty easy to identify. How about the ones on the far side? Would they look peculiar in any way?
Yeah, so that's harder because as I showed in the one slide, kinematically, they look like they belong. It's harder to see how far out, there we go. So kinematically, we're not gonna see, oh, they shouldn't be at this velocity as easily. Another way to really identify them might be through possibly metallicity. So let's say that they were halo gas clouds. Then they might have a lower metallicity than you expect a gas cloud to have coming from the disk. You expect a disk cloud to have a metallicity closer to solar. But if these have a significantly low metallicity, then it's possible that they were halo clouds hanging out and just got rammed into by the Fermi bubbles. If they were from previous outbursts, I'm not sure it would be very easy without some very strong kinematic modeling.
Actually, you might be able to find ones not in front and back, but outside left and right.
Right, yes. The projected velocities for those would be difficult though, right?
Maybe, maybe.
Um,
Hmm.
Hi, Trisha.
Hi.
Thanks a lot for the talk. I was wondering, can you estimate gas masses for these clouds?
Oh, like total gas mass?
Yeah, or ionized gas mass, I don't know.
So we can't, I don't have anything for that though. So we can estimate the approximate levels of ionization and then assume what you would expect to see in ionized gas from what we're seeing in, say, like the silicone. So for silicon, you would add up all of the gas mass clouds from those particular ions that you're detecting and then make assumptions about the ionization levels.
Thanks.
I have what might be a naive question, so you can tell me whether or not this is completely off base, because I'm not even sure if the timelines line up and everything. But just in terms of what could have triggered or created the bubbles in the first place, could you learn anything by trying to associate it with the Milky Way bar and what may have given rise to that in terms of looking at age and that kind of thing? Because as someone who has not studied galactic astronomy or galactic structure, I still have this vague recollection from grad school that bar formation tends to be due to some sort of interaction event or maybe some sort of like star formation. But I could have the causality backwards, so I'll let you correct me if I'm off base.
I don't actually remember the details, but I remember hearing something about the bar being unrelated to the Fermi bubbles, but I would have to look into that specifically because it's been a long time. We have a new postdoc coming in January, DK. He's probably the best resource for that because he actually works on the bar structure near the Milky Way, so I'd have to ask him.
Okay, thanks.
Yeah.
I think, and just chiming in, I think that the predominant theory now is that most bars are not created by interactions. It's just sort of the kinematics of disky structures that can drive bar formation.
Okay.
But it's still not fully known.
All right, any
Trisha,
final questions for Trisha?
can you go back to the plot of GSR velocities versus elevation?
With the,
Yeah,
yes.
or latitude. Is there a similar plot versus galactic elevation B? Is that might, it seems like an easier way to cross-link that last diagram we had with the bubble geometry and the angle you're looking at.
Versus what? Sorry, I didn't hear part of that.
just instead of absolute latitude, to have the angle be on the x-axis.
Oh, you mean just latitude, not absolute latitude?
Yeah.
So I think we actually did look into some plots where we didn't take the absolute latitude. We just plotted the degrees here in latitude. Same with some of the previous plots you saw, but unfortunately with the UV data especially, the data is so sparse that it's hard to look for trends when you don't hold over the scale here to include absolute latitude.
Okay.
Yeah.
All right, any other questions? All right, well, thank you for the talk, Trisha. And we will have our science lunch again next Thursday, who is Jason, and we'll be discussing the GBT observations at Titan. All right, so we will see you all next week.
Thank
All right,
you.
thanks everyone. Thanks for a great
Bye-bye.
talk.
Thank you.
Thanks, Trisha. See
Yeah.
ya.